I have three parts to this talk. The first one will be about impacts in general, just a very brief introduction to set the stage here. The second part will be about the mass extinction at the Cretaceous-Tertiary or Cretaceous-Paleogene boundary, and kind of how do we know what we know, a little bit of a historical approach there, including lines of evidence, and then at the end I'm going to show you some recent results from the Chicxulub impact structure in Mexico. I'm supposed to be boxed in here in this orange or yellowish square here, so I can't move very much, I'm told. Talking about impacts, now what you have just heard from David was a brilliant introduction about mass extinctions and how they might operate and what some of the driving factors are. And the mass extinction he concentrated on, of course, had volcanism as the major cause, not necessarily the effects that were involved in the mass extinction are unique to volcanism, because some of the results that happened, like acid rain and et cetera, also happened from impacts. And that reminds me of something that Doug Irwin from the Smithsonian said a while ago. He said, wouldn't it be boring if all mass extinctions have the same reason? And what I'm going to show you here is one where impact was at least the major component. Now, impacts. First, something about the Earth's place in space. Now, we know all, and I have to admit here, I'm not a paleontologist, I'm a geochemist and planetary geologist, so I deal a lot with extraterrestrial materials, and for those of you who have been at the Natural History Museum in Vienna here, we have the world's largest meteorite display, and meteorites are extraterrestrial material that constantly fall on the Earth, they accrete on the Earth, and we have at present a flux in terms of meteoritic material, smaller dust grain size objects up till meteorite sizes that are on the order of 10 to the 7 to 10 to the 9 kilograms per year. So most of that, of course, is small, but occasionally there might be a larger object in between. Now, what happens when a larger object strikes a planetary surface is it creates an impact crater. And the best place to look at impact craters and kind of look how many are forming per unit area, per square kilometer, whatever you want, in the inner solar system is the Earth-Moon. Because the Moon is a geologically, at least now, inactive body that doesn't have an atmosphere and therefore records faithfully all strikes from outer space. And so what you see here is just some image of the lunar surface that is covered by meteorite impact craters. Interestingly, of course, a few hundred years ago, the main opinion was that these craters on the Moon are of volcanic origin. This is because most people had no idea of meteorite impacts even happening, but volcanoes were a common occurrence in the landscape, and of course Galileo, who discovered lunar craters, didn't have to look very far because in Italy there's lots of volcanoes. So it was actually only in the 20th century that that viewpoint gradually changed, and now we know for a fact that all these crater structures that we see, small and large, on the surface of the Moon have formed by meteorite impact. And the frequency that we kind of observe here tells us how often such impacts occur in the Earth-Moon system. And the Earth is, of course, not shielded in any way beyond the atmosphere it has that screens out some of the very small objects, but is also subject to the larger impacts, just like the Moon, because it sits in the same area in the inner solar system. If we go around in the inner solar system and look at some other planets, planetary surfaces, the image on the upper left shows you a mosaic of the surface of Mercury, the innermost planet, which is the smallest of the terrestrial planets, but it is covered by meteorite impact craters. It is the dominant landform on Mercury. The image on the lower left shows you a radar image of a crater, an impact crater on the surface of Venus. Venus is a planet, we've already heard that in the first talk today by Ariel, that has a very dense atmosphere. It's about 90 times the atmospheric pressure as on Earth. And it's very intransparent, it's opaque. And so we can't photograph the surface of Venus, so we have to turn to radar. And with radar, we've discovered hundreds of impact craters on Venus, even though the dense atmosphere screens out the smaller impacting bodies, impacting asteroids. Mars, on the upper right, is a planet that is about half the size of the Earth and is covered by impact craters. Its atmospheric density is much less than on the Earth, only about 1/700th of the atmospheric density on the Earth. Therefore, even smaller objects make impact craters on Mars. So, impacts are a very dominant landform on all terrestrial planets. Between Mars and Jupiter in the inner solar system, we have kind of the source of all these craters that we see on the planets, and those are the asteroids. The asteroids are what we geochemists or cosmochemists like to call the leftover of the formation of the solar system, some cosmic rubble that was left over from the time when the planets formed by accretion, by collisional processes. The first minor planet or asteroid was only discovered in January 1st, 1801 by Piazzi in Italy. And in the 19th century, hundreds of asteroids were discovered, mostly by visual means. In the 20th century, photographic methods were added that led to the discovery of many more thousands of asteroids. And today we use automatic cameras, digital cameras, and that have led to our currently knowing the orbits of close to 1 million asteroids that are out there. Most of them are, of course, small, a few kilometers in diameter. And about 20,000 of those that are out there that we know the orbits of are on Earth-crossing or Earth-approaching orbits currently. So they are in active danger of colliding with one of the planet, either our planet or the moon. But what's interesting to point out, here is one of the largest asteroids. Those are photographs of asteroids that have been visited by spacecraft and therefore photographed. This is a large one, about 130 kilometers across, Lutetia, but there's some smaller ones as well. But what you're supposed to notice here is that even these asteroids are covered by craters, and therefore collisional processes are dominant also between these bodies. They collide with each other all the time. They might break up, smaller objects might get into the inner solar system, the larger ones form craters, the small ones land as meteorites on the surface of the Earth, for example. Now this is what I like to call a cosmic shooting gallery, because this is a fraction of those 20,000 asteroids that I told you that are in Earth-crossing and Earth-approaching orbits. The yellow ones are Earth-crossing, the orange ones are Earth-approaching, but I've plotted here only the ones that are larger than about 1 kilometer in diameter. And we know there are smaller ones. For example, you might remember that just about 5 years ago, in February 2013, a very small asteroid entered the Earth atmosphere and exploded over Russia, a location called Chelyabinsk. And that was a body that was only about 20 meters in diameter. It was not predicted. It came out of the blue sky, and it exploded in 25 kilometers altitude. And the energy of the explosion was about 30 times that of the Hiroshima atomic bomb. Small object, great consequences. And that is one that we can't predict because we don't know the orbits of all these small objects. So this is something we have to think about when we talk about impacts. There's lots of objects out there. What happens when one of those objects hits the Earth? Well, here is one of the most famous impact structures or impact craters on Earth. This is the Meteor crater or Barringer crater in Arizona, not very far from Flagstaff, a little bit east of Flagstaff. It's 1.2 kilometers in diameter. It is a very young crater. It formed only about 50,000 years ago. And it formed by the impact of an iron meteorite, or a small iron asteroid, only somewhere on the order of 50 to 70 meters in diameter. So very small object makes a relatively large crater. This is a young impact structure. And what happens, it's kind of interesting to remember, we have an asteroid or a large meteorite that hits the surface of the Earth or the Moon or whatever you want with very high velocity, and that's the key here. We're talking about velocities that are somewhere between 10 and 70 kilometers per second. So that is a lot of velocity here. And of course, you remember the equation for kinetic energy. It says kinetic energy is 1/2 times the mass times the velocity squared. So if you have these huge velocities, even moderately massive objects become hugely energetic when they transfer their energy into the ground. And so here we have this asteroid penetrating a little bit into the ground, releasing shock waves. That's important for the understanding and identification of impact structures, because these shock waves lead to irreversible changes in the crystallographic structure of many rock-forming and accessory minerals. And that helps us identify impact structures. And then the release wave, the decompression, leads to the excavation of the crater, and then we have an impact structure here, maybe with a small little central uplift, which is the case for larger impact structures on Earth, larger than about 2-3 kilometers in diameter, something like that. And the take-home message here is 2 points. First of all, a small object makes a much bigger crater. The relationship is about 1 to 20, something like that, in diameter, and the whole thing happens within a few seconds, maybe a couple of minutes. So it is a geologically extremely short-term event, much shorter than volcanic eruptions. The effects on the environment can be severe, of course, as we'll see in a moment. Now, impacts have been important in the Earth history throughout. The early Earth, of course, formed because of impacts. We called that accretion. And the very early Earth, during the Hadean, for example, was dominated by impact events. Here is, of course, an artistic rendition. Even though at, say, 4.3 billion years ago, there was already some evidence for oceans on Earth, but impacts were much more important than they are today. When we look back in the early terrestrial record, of course, we have no real rocks of the Hadean. We have a few minerals left, but the first real rock record of impact events is about 1 billion years after the formation of the Earth. We're talking about somewhere around 3.4, maybe 3.5 billion years ago. And one of the reasons, of course, is that we hardly have any rocks that are much older than that. And these very early impact records comprise thick spherule beds that have been shown to be impact ejecta from large craters. Those craters are lost because of erosion, of course, in the meantime. And they are found in southern Africa, but also in Australia, because those are simply the oldest preserved places on Earth. And so this is a couple of images. This is a hand specimen up here in the upper right that shows, here's a 2 centimeter scale bar, lots of spherules that are enlarged here, and they contain an abundance of extraterrestrial metals in the form of, for example, platinum group elements, iridium, osmium, platinum, palladium, and so on, that are enriched here. Those are elements that are very enriched in meteorites compared to the Earth crust, which will be important for the other part of our story here in a moment as well. But the oldest impact structures, impact craters that have been preserved on Earth are actually much younger than that. They're about 2 billion years old. The 2.02 billion year old Vredefort impact structure in South Africa, and the about 1.85 billion year old Sudbury impact structure in Canada. Both of them were very large structures on the order of 250 to 300 kilometers in diameter. What is left of them today is much less than that because erosion has taken a toll since then. But those are the oldest proper impact craters known or preserved on Earth. They're also some of the largest ones that we have on Earth. And so that means, of course, that for about half the Earth history, we have hardly any impact record, and the reason is the paucity of the rock record. Now that brings me up to today a little bit. Here is a map that shows us the distribution of meteorite craters on Earth, the white dots that you see here. And of course, one notices that they are not evenly distributed over the Earth. And the reason, again, is that rocks on Earth are not all of the same age, like on the Moon, basically, which records what has happened there in the last 3-4 billion years. On Earth, not. And it also reflects the likelihood of how impact craters can be discovered. It's very difficult in the African jungle, for example, but much easier in the Sahara Desert, where they stick out much more. It's a question of preservation, it's a question of rock record, it's a question of how to find them, it's a question of erosional status, and it's also a question of how intensely people look for them. There have been a lot of crater search programs in Finland, for example, or in Canada, but much less so in some other countries. And so this reflects this uneven distribution of impact craters that we know today. The one that we're going to concentrate on in a moment here is this one right here. Anyway, so today what we know and understand is that the importance of impact cratering as a geological process on the terrestrial planets is fairly obvious from how many we actually see on the surfaces of these planets. If we kind of go back a little bit in history, let's say in the 1970s, at that time only about 50 impact structures or craters had been recognized on Earth. Today we know about 200. And the studies of impact craters and of shock metamorphism was mostly restricted to a few mineralogists, a few geochemists, who worked on, for example, lunar rocks. Because rocks brought back from the Moon had a lot of these impact records in them. And impact cratering was not really a part of any geological curriculum that was taught at any university, because it was not seen as a major process at that time. And that is not that long ago. That's just about, 40 years ago, something like that. And so part of why this story, also of the acceptance of impact craters as a geological process, has changed is because of these two guys here. On the left side, Luis Alvarez, on the right side, Walter Alvarez, a physicist and a geologist, at the famous Gubbio Cretaceous Tertiary, now Cretaceous Paleogene boundary site. Here is this is a later image, but this is a earlier one in 1979 at a similar section that shows Walter Alvarez there. And what they basically discovered, it was a chance discovery. Walter Alvarez was looking for methods how to date the rock record there in Italy, because he was interested in tectonic movements and wanted kind of to know how fast certain things happened there. And the idea was that they could use the accretion of extraterrestrial material, which I've mentioned at the very beginning of this talk, happens all the time, rains down at a constant pace, to use some of these rare trace metals that are common in meteorites but rare on the Earth as a proxy for the accretion of extraterrestrial material, and therefore, if you have a lot of extraterrestrial material in a particular rock section, that means that rock accumulated rather slowly, and if you have very little in it, it's diluted, that means that rock section accumulated rather rapidly, and that was the general idea. And they measured also kind of more or less by chance also the boundary rock between those two units, the Cretaceous and the Tertiary. And in there they found, again, they were not looking for this, but they found kind of by chance enormous enrichments of these platinum group elements, which again are common in meteorites but rare in terrestrial rocks. And they kind of looked around first for possible supernova explanation, and then they settled on the idea that maybe there was a large-scale impact. And this was published in 1980 in the journal Science, Extraterrestrial Cause for the Cretaceous-Tertiary Extinction. Around the same time, there was a separate paper by Jan Smit and colleagues in Nature that came more or less to the same conclusion from analysis of a different rock section somewhere else. So this was the idea. And of course, this was the smoking gun, as they kind of indicated. But this was not without any controversy, and it still is a controversial idea. But the point is that now, after so long, we've accumulated a lot of evidence that an impact really did happen at that time, and it had some catastrophic consequences. So what is the evidence that was accumulated? And especially early on, let's say the first 5 years or so of that hypothesis in the early 1980s, was resting solely on the enrichment of the platinum group elements and other siderophile elements within that boundary section, and interelement ratios of these elements that were equal to those found in meteorites and unlike those found in normal crustal rocks. Later on, some more evidence accumulated, and I'll talk about that in a moment, but geochemically speaking, there was a lot more that was added to kind of that line of evidence, in that some isotopic studies were found to also present rather irrefutable evidence of an extraterrestrial component. And that was the study of the element osmium, which has a very distinctly different composition in meteorites compared to terrestrial crustal rocks, that showed a clear presence of an extraterrestrial component. So not only the abundance, but also the isotopic ratio indicated that there's an extraterrestrial component. And later, when measurements were possible for that particular element, chromium isotopic data also supported an extraterrestrial component, and in fact were even possible, because they are different, the chromium isotopic ratios are different between different meteorite groups, pinpoint that it must have been a carbonaceous chondritic composition of this impactor. And then of course we had a lot of evidence for soot and charcoal, and so pointing towards a lot of burning going on. This is a little complicated here, but it just shows the geochemical evidence. On the bottom here, I have a diagram that shows an osmium-isotopic ratio diagram, where we plot the radiogenic isotope osmium-187 compared to a variety of other parameters. And the only important thing is that in this diagram, we're clearly able to distinguish between meteoritic compositions and typical terrestrial compositions. This is an example from an impact structure that shows a variety of impact rocks that have clear extraterrestrial components, especially down here. This one not so much, but only a little bit. You can also look at the osmium isotopic record in the Earth oceanic sediments. Here plotted by age, shows very clearly the KT impact 66 million years ago, but also the late Eocene impacts about 35 million years ago that led to a change in the isotopic chemistry of water and therefore of the sediments. This is a plot of chromium isotope normalized epsilon 53 chromium isotopic composition that shows that terrestrial rocks are all at 0. Then here we have some ordinary chondrites, for example. There's some craters that have ordinary chondritic impactors. And then here are these South African spherule beds, for example, from the early Archean and the KT boundary ones that clearly indicate that they are similar to carbonaceous chondritic compositions. But what was also found in the 1980s, mid-1980s, was not only geochemical evidence, but also evidence for shocked minerals at the Cretaceous-Paleogene boundary. And here is just an example of some shocked quartz grains, a few colorful images. Some of them are taken with a microscope here, and this one on the lower right is taken with an electron microscope of a whole grain that has been etched and clearly shows the development of the so-called planar deformation features that penetrate through the whole grain in this case. And the orientation of these planar deformation features relative to the z-axis of the quartz grain and their abundance of the various orientations gives us a hint about the shock pressure. Such shocked minerals form in natural processes on Earth only in impacts because they require pressures that are orders of magnitude higher than any other endogenic geological processes would provide. So this was fairly clear evidence then that an impact did occur. We had shocked minerals, of course, not only shocked quartz, but also shocked feldspar and plagioclase and shocked zircons and so others. There's impact glass, there are impact-derived diamonds, there is spinel that is extraterrestrial, and so on and so forth. And this is a map that is already a few years old, but it shows a number of KT boundary sections where all this particular evidence has been found. So it's kind of a worldwide thing. And this shows a close-up of the KT boundary layer. Here we have the Cretaceous rocks, and there we have this kind of 2-3 centimeter thick layer of impact ejecta that had later been altered and contain a massive extraterrestrial component, but also shocked terrestrial minerals. And then later on, here we have the tertiary rocks, now called Paleogene rocks. This is in a location at the Raton Basin in Colorado, which is a terrestrial boundary section, as opposed to the ones in Italy that are marine boundary sections. So at these terrestrial boundary sections, we see that the boundary layer consists actually of 2 layers. There's a lower kaolinitic layer, which is probably altered or weathered distal impact ejecta, and an upper smectitic fireball layer, which has the shocked minerals, the magnesium-ferrite crystals, the high abundance of platinum group elements, which probably originated from a cloud of vaporized bolide, and also some entrained target material. And this is important also for our understanding of this. Now, what happened when you have a large impact like this is, of course, you have all kinds of nasty things happening, and they're somewhat similar to the list that David showed earlier. We have acid rain, we have a thermal pulse, we have carbon dioxide going into the atmosphere, et cetera, and I'm not going to go through this in great detail because I have another slide a little bit later that talks about some of these effects as well. It took about 10 years after the discovery of the evidence that there was an impact at the KT boundary that the respective impact crater was found. And that tells you a little bit about how difficult it is to find impact craters on Earth. And the point, of course, is that this is a damn large impact crater. We now know it's about 200 kilometers in diameter, and even such a large impact crater is not necessarily obvious on the surface of the planet, even if it is geologically as young as just 66 million years. The reason is that it is mostly covered by younger rocks, and the location of this structure, here is the Yucatan Peninsula, here's the town of Merida, And this is a gravity anomaly map that shows this, but on the surface, almost nothing is visible, certainly no impact crater as we know it, like the one that I've shown from Arizona earlier on. So it actually needs geophysical methods to determine the complete layout of the structure, which a structure this size, about 200 kilometers in diameter, is fairly expensive. And it requires drilling to get down through the about a kilometer thick layer of post-impact sediments and crater fill that has accumulated with time to get at the impact rocks to study them in great detail. And drilling is even more expensive than geophysics, but I'm going to show you a little bit of an example of that later on in a moment. Now, in the early 1990s, finally, some samples were located, some drill core materials were located. It was found out that this crater material has the exact same age as the Cretaceous Tertiary boundary, but also, and that is maybe even more importantly, that the geochemical fingerprint of rocks found within the crater and of certain trace minerals is identical to that of impact glasses, for example, or some shocked minerals found at distal sites throughout the world, and therefore clearly linking the two events together. This also represents one of the largest, if not the largest, impact crater, at least that we currently know, in the last several 100 million years on the surface of the Earth. So the point also is that this was a rather rare, I wouldn't say unique, because it happened other times, but a rare event in Earth history that we had an impact of that magnitude. And I should add, in a rather unpleasant territory, because the impact happened in a location where there's lots of carbonate rocks, lots of evaporites, which helped putting a lot of nasty things similar to what volcanoes can emit into the Earth atmosphere. This is some of the patterns of the ejecta from the immediate crater site. And here we see what happens if we go away from proximal sites. We have very thick ejecta units to thinner units to distal ones where it's only a few centimeters thick. Now, within the last few years, there has been a big effort to drill the Chicxulub crater. I should add that some of the drill cores were done early on by Pemex, the Mexican oil company, already in the 1960s, and there is very little material left over from that. Really, it's only a few hand specimens. Then there was some shallow drilling that was financed by Mexico, by UNAM, the university in Mexico City. And then there was a deeper drill core near the center of the structure financed by ICDP, the International Continental Drilling Program, about 20 years ago, a little less than 20 years ago. The problem was that this was in a location where it was difficult to reach some of the materials that would have been interesting, I would say, for us impact scientists, namely the melt rocks. So a new drill program was conceived, this time as a collaboration between IODP, the Ocean Discovery Program, and the ICDP, the International Continental Drilling Program. This one was supposed to happen in the so-called inner ring, and I'm going to show you what that means in just a moment. But this drilling program finally happened in 2016. Here is the outline superimposed on one of these gravity maps. So here we have the so-called inner ring, and then we have the outer ring or crater rim. And this is with the drill rig that was used, a so-called lift boat. The drill site was offshore at a very shallow water depth. This is the idea to drill in this location is because the basement rocks, through cratering mechanics, have been uplifted to relatively shallow depth and therefore make them accessible to drilling. In the inner part of the crater, the basement might be 10 kilometers or something, or 8 kilometers down at a very deep depth, whereas here they're only about a little more than 1.5 kilometers deep, and therefore more accessible to drilling. The coring happened, as I said, in 2016, was completed May 26 there. There was the coring going to depth, and this was the target site. And up here on the upper right, you see kind of a cross-section of the crater, how it was imagined or is imagined. There is, this is a large enough structure that doesn't have one central peak, but it actually has a central peak ring structure. And so here we have these basement rocks uplifted to where they can actually be drilled. And of course, there are some post-impact rocks that tell us about how life returned into the crater and so on and so forth that were also studied in this respect. I'll skip this one because this is not so important. Now here is some of the rocks that were found. This is an artist's image of the structure that shows kind of shortly after the formation how this inner ring might have looked like. And interestingly enough, so the post-impact sequence was cored between about 600 and 620 meters below seafloor, and then the upper peak ring rocks were reached at 620 meters, and then we have lower peak ring rocks. And all these rocks contain a lot of impact breccias, very interesting material that are currently still being studied. And we have just in about 2 months from now a big workshop in Mérida in Mexico where people who are involved in this drilling project are going to get together. But what happened in such a large impact event, and I'm getting close to finishing up here, after the impact about 1 million tons of soot went into the atmosphere. There was little or no sunlight that reaches the surface of the Earth for about a year. Photosynthesis is impossible. It cools quite considerably. We have what is called an impact winter. But of course, in the upper atmosphere, we have heating of the atmosphere. That, together with a massive injection of water, destroys the stratospheric ozone layers. So therefore, the Earth's surface receives high doses of ultraviolet radiation for about a year, maybe a few years. Temperature remains above freezing in the oceans, parts of the tropics, but photosynthesis is severely inhibited for the first years after the impact. And therefore, this is one of the reasons or these are several of the reasons that helped cause a mass extinction in this particular case. This shows some of the temperature changes that happened, and the main thing is that we have basically a huge amount of freezing going on within a relatively short period of time within shortly after the impact event. Oops, what happened there? Oh, there we go. Summary. So the debate that followed the suggestion in the 1980s that there was possible evidence of an impact event in the 1990s and in 2000s led to the more general realization that impact cratering is a very important process on the Earth as well, and not only on other planetary bodies. There would be no reason to assume that the Earth is immune from whatever shapes the surfaces of the planets around it. And of course, for the past few decades, planetary scientists and meteoriticists and so on, who work with the products of impact cratering like on other planets, they have grown to accept impact cratering as a normal geological phenomena, whereas, and I cite here David Raup, that was already mentioned earlier, another group, the paleontologists, is confounded by what appears to be an ad hoc theory about a non-existent phenomenon. It's because they were just not used to that. Nobody taught them that impacts existed. And on the other hand, the meteorite people, they said, of course, impacts happen all the time. We see it, it happens. So finally, I think these groups are converging somehow and are accepting each other's evidence here. And what we have here is evidence that a large-scale impact event coincides exactly with a mass extinction. The line of evidence for that impact event is overwhelming. And of course, I would just formulate it rather simply and say the effects of the impact event were particularly nasty for quite some time, and therefore I would posit that it was the major cause for the mass extinction at that time. I would like to add that what David said is entirely correct, that, for example, at the Permo-Triassic boundary, we have no evidence for an impact event. And I think what that means is not every extinction event has the same reason. And so nature is diverse. Let's accept it, let's study it, and let's get some enjoyment out of it as well. And thank you very much for the attention.